Yeah, so I have about 40 slides in 15 minutes, so we're going to see how this goes. When you work at Princeton for the past 8 years and you have to explain to your wife that you're leaving for 12 hours to start up a gas compressor, and what do you do after you start up a gas compressor? You go have beers. So you come home after that, you know. So you have to put a lot of slides together to convince her that you're actually doing work at Princeton. So I'm going to skip through a bunch of slides because I'm going to try to keep it to 15 minutes. So Princeton does have a lot of money, and I think some people mentioned that, but they do try to be honest, or they actually are honest with the project metrics. So the return on investment for any of the projects has to be within 5 years, and the energy rates are really low because they're very aggressive with market side and a lot of little tricks on demand reduction and stuff like that. So they're about at 6 cents per kWh. So to try to hit a 5-year payback at 6 cents is very challenging. I'm going to talk about a little bit about the process that we go through as part of the project implementation. So the first part is an investment grade audit. So we screened probably, I'm focusing mostly on the central utility plant because that's where we did work. So I'm sorry, home and lighting guys out there. This will be very boring for you. So we start with an investment grade audit, and what that does is we do a lot of the stuff that some of these other guys were talking about with determining what the savings are going to be. So we started off with spreadsheets probably 15 years ago, and now we're utilizing neural nets and other machine learning. So we've actually learned that we have to keep a spreadsheet in parallel to that other process, just because anybody that's auditing, you're going to try to explain how a neural network works, and it doesn't go over that well. So you're going to have to keep a spreadsheet in parallel to some of that work for the optimization process. So we do an investment grade audit, which some of the projects fall out of because the payback's not great enough. So if the utility rates ever go up, we'll reevaluate, or Princeton will reevaluate some of those measures. And then we run this custom plant performance model that takes into every aspect of Princeton's plant's actual operation. So all of the efficiencies of the components as weather changes, as condenser water temperatures change, and then it'll spit out actual savings per piece of equipment. So the top kind of this is where we are stuck with our legacy spreadsheets. So the top kind of summarizes each piece of equipment, its energy consumption and its energy cost, and then the bottom shows what that savings and cost will be after the implementation is performed. I picked a great one here down at the bottom right. It says, do not implement this measure, so that's a red no. I don't know what that was, but it's just as good to know what not to spend money on than to what to spend money on sometimes. So one of the big things that we've learned is that these are more complex custom measures, and they require a lot of training. And if we've gone through the 500 projects that we've implemented at Princeton and at other customer sites, the ones that are more successful are the ones where the customer is willing to train on and train the staff, train the maintenance staff. We go back to these projects to perform training, and we find that it's just put in manual and you're not getting any savings. So we actually flipped it, and we started doing this at MIT, and we do training up front. So it kind of flushes out any operational issues that you see. So we train before we actually implement, and we do this at Princeton now. The process is very data-driven. So here's an example of a chiller efficiency map. So this is utilized within the training process, as this is a lot of data, and it's data visualization, right? So we use this data within the optimization process, but it also is good for the operators to see, hey, don't operate in the green, don't operate in the red. And then here's an example of operation pre and post optimization. So a lot of the projects that we do in the central plant where equipment's very expensive, controls optimization is usually your lowest hanging fruit, because you can change a line of code and take the equivalent of 10,000 houses off the grid with one line of code and a controller. And we'll get to some examples here. So we do fundamentals training on the pieces of equipment. So this is a slide from training we did at Princeton. So here's some sample projects that we did at Princeton. So we did boiler feed water pump optimization. So the boiler feed water pumps feed the cogen system, which is an LM 1600 gas turbine, about 15 megawatts of output, depending who you ask. GE 15, obviously. But so what we did for this project is we replaced the existing boiler feed water pumps, which were a operational nuisance. We installed new boiler feed water pumps, and we operate them on a VFD. And there was really good savings. The set point that controls these pumps was set kind of artificially high, and we didn't get our savings initially. So through consistent ongoing training of the personnel, we showed them how to lower it, and then we just automated. Princeton's a very manual plant, and they want to stay manual because they want to keep the operators sharp for when Sandy comes. They actually had a little bit of a hiccup, but because the operators responded really quick, they didn't go down. So they like to stay manual, but after they've ran it in manual and they've trained and they said, okay, we don't need to run that in manual anymore, we'll automate. And so the pressure reset on these boiler feed water pumps was manual at first, and then we automated it. They have a 7-element duct burner for the gas turbine. So I think this is the only project in the world that this has been done on. So Princeton's also a little cutting edge. So they used to have a single valve controlling the gas flow to this duct burner. We modified it to put control valves on each element, and it allows them to have increased turn down on the gas burner, which saves a tremendous amount of energy. So they have a 1,250 horsepower gas compressor that feeds gas into the combustor on the gas turbine. We did optimization on this gas compressor, and we dropped about half a megawatt. So that's half a megawatt of parasitic load, and it's running at full load during the hottest days of the year, which is when we need load reduction. So optimizing this gas compressor significantly reduced load on the grid, and that's equivalent to like 5,000 houses, taking them off the grid. And that was just a few lines of code. We had to beef up the reliability because the gas compressor kind of just ran constant, and now we're varying it. So we did have to do some resiliency upgrades as part of that project. The great thing about Princeton is they really understand the equipment. We go to some sites, they don't touch the gas compressor. I don't want it to trip. We trip the gas compressor at Princeton, which it's going to happen. You're going to trip equipment. And, oh, don't worry, we'll get it back up. We understand the safeties that are in place. That high temperature safety is the first safety to go, high pressure safety, and then there's a relief that's a final safety after that. So if we trip it, it's not the end of the world. And that's really allowed them to do a lot of this stuff that's like the only place it's been done. So here's an example of the TES system. Secondary, my slides got messed up. So this is the secondary chilled water pumps for the TES system. These are 400 horsepower pumps. There's 4 of them. So this is an example of controls optimization. This is data representation of what a pump looks like on a VFD. So before, they'd be running 3 of these 400 horsepower chilled water pumps, and the common, oh, I have a VFD, it's saving energy. Yes, it's saving some energy, but you're running at a very inefficient point. It's 56% efficient, and total energy consumption is 375 kW. So what we did is, which is counterintuitive to operators, so you got to train on this. We actually turn on a 4th pump in this operating mode. This actual test data. It moves to the left of the curve, and I get closer to what's called BEP, or best efficiency point of the pump. And my efficiency went from, it was 56 and went up to 76. So 115 kW reduction with 2 or 3 lines of ladder logic. And so you're taking hundreds and hundreds of houses off the grid with a line of code, and without it running that way, it's ran that way for 10 years prior to us making these changes. So that's that negawatt that we're talking about. Here's an example of the power consumption for those pumps. So in between the red, or just prior to this first red line pre-optimization, that's how the pumps ran before we implemented the control logic. In between the 2 red lines is after we had implemented it, and you can see a night shift operator takes it and puts it into manual. You can see that spike back up. So we look at this, and then we do training, and post-training, you can see that there's a significant reduction. But if we just walked away after we implemented this, took our checks, said, thanks, Princeton, it would probably revert back to almost exactly how it was before because they don't understand it. It trips. And what happens with the training is we learn a lot too. We say, oh yeah, that works. And the guy says, no, it doesn't work. And we, yeah, it does. And then we go down and we're like, yeah, it doesn't work. Okay, let's fix it, right? So that it keeps working. So there's a 4,500 ton steam turbine chiller. There's a few steam turbine chillers, but this is kind of the workhorse for the plant. So there's a big piece of equipment that's like 20,000 houses equivalent. I'm trying to give some equivalent numbers to the energy consumption here. This 4,500 ton steam turbine chiller, we did an optimization package on it. So we're modifying the OEM components, and we actually had the OEM bid on this job, and the OEM lost the project. So we ended up doing, so some of the things that we did are turbine hand valve optimization, improved refrigerant level control, improved refrigeration migration, heat mass balance with torque telemetry, and reactive surge control. So with these projects, these are all went through the custom incentive process. So you can imagine there's a long dialogue with the program to get on the same page about what reactive surge control is going to do. So what we ended up doing a lot is like, hey, we'll stand behind this stuff. Let's just do M&V on it because I think it's going to take less time to just do M&V. So for all of these projects, we did a pretty intense M&V. And here's an example of some data to show the M&V. So the map up at the top, so the colors at the top, that's how it ran prior to this modification, this chiller. The map at the bottom, more green is better, is how it ran after. And then the very bottom is the differential. So that the heat map shows that throughout that chiller's entire operating range, it saved energy, and a substantial amount of energy. And that's all NIST traceable instrumentation to do a heat mass balance on that machine. TES optimization, there's a free cooling heat exchanger that we implemented under the program. So that's actually cooling TES water, free cooling thermal energy storage water. So what do we do after we implement? We do more training, lots of training. And then sometimes we do connected services. So this is gonna get into some of that machine learning and AI. So this is an example. I think this is Microsoft Azure, so we'll use the Azure platform. But what we'll do is, here's an example of what we were talking about. Here, on the left is how we used to do things for MIT, and that's a regression model, right? So on the right is a machine learning model, and what that does is you say, hey, what was this blip that happened? In a regression model, I have to feed it all the data to make the prediction. In a machine learning model, it will see that there's a solar eclipse and say, okay, on a solar eclipse, the heat load goes down because people leave and go outside and look at it. But I don't have to feed, hey, there's going to be a solar eclipse on this day. As long as it's getting that data, it's going to machine learn that kind of stuff happens. So you can see blue and orange on this graph on the right, and one is our machine learned predictive model, and one is the actual energy consumption. So what this does for MIT is if something goes wrong in that building, my machine learned model is not going to match up with the actual building, and we can go hit it really quick and find out what's wrong before time has elapsed. And we got to try to sell this to Princeton here pretty soon. So the post optimization is training and tuning, and this is a very difficult process that just takes if you're getting sold a magic pill or a silver bullet, the closest thing to that is like changing out your LEDs. And anybody that does that knows that's a super challenging process. So any energy savings that you're going to do in a facility is a very challenging process and takes a lot of work, I think. And I'm glad that these guys give us some funds to help out that process. I think that's all I have. 15 minutes? Yeah.
Anyone have any questions for Travis?
Questions?
Questions? Thank you very much. That was very informative.
Yeah, I think you should have been the closer. I don't know if I can really follow that one. I'll try though.